Welcome to Distant Curve Remote Area Telecommunications Severe Weather Analysis. Today is Sunday, January 18, 2026, and we are diving into the atmospheric conditions affecting Brisbane. If you find this analysis helpful, please like and subscribe to support continued severe weather analysis. Let's break down what the morning atmosphere is telling us about the day ahead. Looking at the morning sounding from 10 a.m. local time, we can see some interesting dynamics at work. The mixed layer CAPE sits at 956 joules per kilogram, which is just shy of the Australian severe threshold of 1000. Surface-based CAPE is significantly higher at 1695 joules per kilogram, indicating that if we can break the lid holding everything down, there's considerable fuel available for storm development. The mixed layer parcel shows a minus 5.0 degrees Celsius lifted index, telling us this air is quite unstable once released. Looking at the wind shear, we have 16.4 meters per second of 0 to 6 kilometer shear, which sits right at the Australian critical threshold of 15 meters per second. The low-level wind shear of 4.2 meters per second in the lowest kilometer is relatively weak. The lifted condensation level is sitting at 682 meters above ground level for the most unstable parcel, which means storm cloud bases would be quite low, allowing hail to grow to substantial sizes before melting. We also see a shallow inversion between 740 and 720 hectopascals, which is a thin cap that could be easily broken. The precipitable water is 44.5 millimeters, indicating abundant moisture in the column. Overall, the morning atmosphere shows the ingredients for organized severe weather if they can be properly organized. Now let's watch the transformation as the afternoon heating takes place. The enhanced sounding shows multiple parcel paths, giving us a fuller picture of where energy could come from. The blue shaded area shows the CIN, that lid we talked about, while the red and pink shaded areas show the CAPE, the fuel available for storms. As the surface heats to 27 degrees Celsius, the mixed layer CAPE decreases slightly to 876 joules per kilogram, still near the threshold. However, the most unstable CAPE remains substantially higher at 1695 joules per kilogram, meaning the stronger storms would come from elevated parcels rather than surface-based convection. The key change is that the CAP weakens with heating, making it easier for storms to initiate. The lifted condensation level drops to 646 meters above ground, further lowering cloud bases. Wind shear remains consistent at 16.4 meters per second in the 0 to 6 kilometer layer. The low-level lapse rate remains favorable for storm organization. What we are seeing is a classic setup where afternoon heating removes the suppression, allowing organized multicells to develop with the potential for rotating updrafts. The 0 to 3 kilometer CAPE of 202 joules per kilogram provides a favorable environment for rapid updraft acceleration. Let's examine the hodograph and wind profile, which tells us crucial information about storm organization and movement. The hodograph shows a strong wind profile curving from the surface up through 6 kilometers. Notice the color progression from blue at the lowest levels through green and yellow at mid-levels, indicating an increasingly strong wind profile with height. The right mover vector points toward the northeast, meaning if supercells develop, they would track toward the northeast at approximately 20 kilometers per hour. The left mover vector points toward the north-northwest. The vector magnitudes show the shear is organized with a steady increase in wind speed with height, which is favorable for organized storm development. The 0 to 6 kilometer shear of 16.4 meters per second, combined with 1.2 meters per second of 0 to 1 kilometer shear, indicates strong mid-level shear with weaker boundary layer shear, a favorable configuration for updraft rotation. The effective shear magnitude is 9.5 meters per second, and the effective storm relative helicity is 146 square meters per second squared. For emergency services operations, this wind profile suggests if storms do develop, they would organize into rotating multicells capable of producing widespread damage through severe wind and hail. The northeast tracking direction points toward inland areas north of Brisbane. Electricity restoration crews should consider prepositioning in northern Brisbane suburbs given the wind profile, though thunderstorm initiation remains uncertain. The atmospheric refractivity profile reveals critical information about downdraft intensity and atmospheric layering. The most striking feature is the superrefraction layer extending from about 6,800 meters down through the mid-levels. This indicates areas of very strong horizontal wind shear and potential radar propagation anomalies. Below this, we see elevated duct conditions around 3,100 meters, which can trap atmospheric moisture and enhance boundary layer processes. Looking at the overall stability structure, the mid-level atmosphere from 2 to 5 kilometers shows moderate stability, which is adequate for both updraft and downdraft development. The DCAPE of 1,357 joules per kilogram indicates strong downdraft potential. The dry subcloud layer at the surface creates an environment where evaporative cooling from precipitation can generate substantial downbursts. The DCAPE velocity of 52 km per hour suggests microbursts could exceed 100 km per hour near the surface if strong convective downdrafts develop. The atmospheric profile particularly supports intense microbursts in the dry subcloud layer. For emergency services, this has critical implications. If strong downdrafts develop, localized severe wind damage exceeding 100 km/h is possible. Fire services should be alert for dry microburst potential, as concentrated dry downdrafts can spark grass fires by igniting dried vegetation. The combination of DCAPE and the low LCL means hail growth will be enhanced through the deep layer of supercooled water extending from cloud base near 680 meters up through the freezing level at 4,500 meters. Looking at tomorrow morning's ML forecast from the machine learning model, we see CAPE at 85 joules per kilogram, quite subdued compared to today. Surface-based CAPE is 173 joules per kilogram. The 0 to 6 km shear jumps to 50.3 meters per second, representing an extreme wind shear profile. The LCL is at 916 meters above ground level. The STP index sits at 0.07, indicating very low tornado potential. SEP is at 0.06, suggesting minimal organized severe weather potential. The storm mode is subconvective due to insufficient CAPE to sustain deep convection. Under these conditions, if storms do develop, they would be short-lived single cells with minimal severe threat. The atmosphere lacks the fuel needed for organized severe weather despite the strong wind shear. The afternoon ML forecast for tomorrow shows CAPE increasing slightly to 98 joules per kilogram. Surface-based CAPE drops to 0, indicating very stable conditions at the surface. The 0 to 6 km shear remains extreme at 57.9 meters per second. This is an exceptionally strong wind profile. The LCL is at 916 meters. The STP index climbs slightly to 0.12, still indicating low tornado potential. SEP is at 0.16. SHIP reaches 0.49, and the 700 to 500 millibar lapse rate is 3.9 degrees Celsius per kilometer. Despite the powerful wind shear, tomorrow's atmosphere simply lacks sufficient instability to support organized severe weather. Storm mode remains subconvective. This represents a critical difference from today. Shear alone does not produce severe weather. You need both energy and shear working together. Tomorrow has wind but no fuel. Always consult the Bureau of Meteorology for official severe weather warnings and forecasts. This analysis is provided by Distant Curve Remote Area Telecommunications. If you found this helpful, please like and subscribe to support continued severe weather coverage for remote Australia. Thank you for watching.